Last time I came here, I think it was 2012, I was a graduate student and I gave a talk here. Hopefully today's talk will be better than that one. But anyways, thank you for sticking around till the end. I'm going to talk about Wreath Macdonald difference operators. So this is joint work with my colleague, Mark Shimizono at Virginia Tech. And so I'll refer to this as OS in the talk. And this is very recent. It was just posted to the archive last night. Right? So it's actually not available yet. It'll be available tomorrow night. And also related joint work, second joint work with Mark and Josh Wen, who is a postdoc at Northeastern. And this one is more in progress, but related. Okay, so what we're trying to do is give an explicit construction of these things called Wreath Macdonald polynomials. So these really arise from geometry of Hilbert schemes. They're a generalization of type A Macdonald polynomials. And until now, there haven't really been explicit methods to deal with them. They're sort of mysterious objects. So that's the point of these works, is to make things more explicit. So for the talk, I'm going to start with usual Macdonald polynomials for a little bit, and then talk about what we did for Wreath Macdonald polynomials. So Macdonald polynomials really started with the Macdonald difference operator. This is the origin of the subject. So I'm going to write this down. M is the sum, k equals 1 to n. N is the number of variables, okay? And it's a very explicit difference operator. So there's a rational function here. L goes from 1 to n. L is not equal to k. And you have parameters q and t. So we have tkl, tx k minus xl divided by xk minus xl. So that's a rational function. Somehow you can think of interacting particles if you like. This kind of has its origins in integrable systems, but I won't talk in much detail about that. So that's a multiplication by a rational function, and then there's this Q shift operator. So this is like a discrete analog of a derivative. So I take a function in n variables and I shift the kth variable by q. So if you like, you can think q is a non-zero complex number, say, and t also. Or you can think it's like an indeterminate, like an abstract parameter. Okay, so this is an analog of derivative, and this is an operator, and it preserves this space of symmetric polynomials. So here's the abstract way to say what the coefficients are. So they're rational functions in q and t. And then we have these variables and invariant with respect to the symmetric group. So permutations of the variables. So Macdonald's major results for the foundations of Macdonald theory states that this operator acts diagonally on symmetric polynomials. It has an eigenbasis. So M acts diagonally on lambda n. with eigenbasis p lambda. So if you've worked with symmetric polynomials, you know that any of the natural bases are indexed by partitions. Okay, so the index here is a partition, an integer partition with at most n parts. And these polynomials are, if you just say that you have an eigenbasis, it's not determined uniquely. So they're made unique by making them monic. Such that p lambda is x1 to the lambda 1. It has this leading term with respect to monomials. So just the monomial built from lambda. And then its orbit under the symmetric group. You have all those terms. And then you have some lower terms with respect to a partial order called dominance order on partitions. Okay. So these are called Macdonald polynomials. So the p lambda Macdonald polynomials of type A, or really of type GLN. Okay. So there's a more general picture in sort of the classical theory of Macdonald polynomials where you can use a reductive group. Okay. So here this is for GLN. And that point of view offers sort of one of the original sources of motivation for doing all this, which is that these polynomials are related to all these families of orthogonal polynomials that come up from representation theory. So Hall-Littlewood polynomials, Schur polynomials, the characters, and spherical functions in the case of symmetric spaces. And so that's sort of the main input for this, what I call the classical theory of Macdonald polynomials. But in type A, there's another reason that we really care about these polynomials a lot. Now, let me show you an example first. So here's what they look like. So P20, let's say our partition is 20. So I have two variables and the partition just has one part. So this one looks like this. So you have this leading term, x1 squared, x2 to the 0, x2 squared. And then you have one really non-trivial term here. And I've got to look at it because I don't remember it. 1 plus q, 1 minus t. One minus qt. Okay, so I'm just writing this down to show you kind of what they look like. One thing we're really interested in studying Macdonald polynomials is what are these coefficients? So they're not random rational functions, they're very structured objects. And these rational functions that come up as coefficients have many nice properties and interpretations that are connected to combinatorics, geometry, representation theory. So I don't have time to spell those out really, but I wanted to at least show you what these things look like. Okay. So I was talking about the general reductive group sort of generality, but in type A, there's another reason we care a lot about these is because they're related to Hilbert schemes of points in the plane, which are geometric objects that play a very important role in geometric representation theory and related fields. So this was really Heyman's insight, Mark Heyman's insight on the subject of Macdonald theory, was that there's a connection here. So what is this Hilbert scheme? So Hilb n C2. Yeah, n is fine. So this is, there's a general theory of Hilbert schemes, not just of points, but the basic idea is that these are schemes that parameterize subschemes of a given thing. So this particular Hilbert scheme parameterizes collections of n points in the plane. Okay, so you should think you have, it's really C2, but you have some n points in the plane, and they can be repeated with certain multiplicities and so on. And this is supposed to give you a nice way to parameterize these objects. So at the level of points, you say that these are ideals. So that's what a point looks like, where the dimension of Cxy over I is n. Okay, and basically this is, if you think of that collection of points as a subvariety of the plane, this is its vanishing ideal. So that's what's supposed to be going on. Okay. So it turns out this Hilbert scheme is a smooth variety in this case. It has that structure, and it provides a resolution, a particularly nice one, of a quotient singularity. So C2 to the n mod Sn. So if I just wanted to naively say, what are collections of points in the plane unordered, I would say the bottom thing, right? So I have a list of n points, but I don't care about the order, so I quotient by Sn. Well, this is singular. So when points collide, when you have repeated points, you get singularities. And the Hilbert scheme, it provides a resolution of this. So that's what it does. So just to give you an idea of a point upstairs that you don't see immediately downstairs. If you have a partition, so I'm not going to care about the size. So this is a partition. I'm not going to care about the length, but the size is, so the total number of, well, I said it doesn't stop. So the total number of boxes, okay, let me clean that up a little bit. Okay, so is n. Okay, so that's the connection. So a partition of size n, any length, well, can't have length more than n, I guess. Then this gives you a point upstairs in this Hilbert scheme. So there's an ideal I lambda, which is a monomial ideal. So it's generated as an ideal in the polynomial ring in two variables by x to the lambda 1, y to the 0, x to the lambda 2, y to the first, and so on. And so this is an element of Hilb n. Okay. And you don't really see this downstairs because it sits over, where do all these polynomials vanish? Just at the origin, right? So this sits over, I'll just write it like this for the sort of equivalence class. Okay, so the n tuple where all the points are the origin. Okay, these are special points in the Hilbert scheme. These are the torus fixed points. So there's a two-dimensional torus acting on Hilb n. It just comes from the natural two-dimensional torus that acts on the plane. Okay. And these I lambda, I would say lambda is a partition of n, are all T fixed points. So the Hilbert scheme is smooth, and you can use methods like localization to study its K-theory and cohomology. And so these are particularly important elements, these T fixed points here. So, okay, so here's Heyman's insight into the subject, into Macdonald theory. So back to Macdonald theory, Mark Heyman, around 2000, I believe, late 90s for sure. Is that, so here, there's an abstract way to say it, which I feel like I need to say to give it, to do it justice, okay? So I'm just gonna write it, but not really explain, because might not even be I'm definitely not the best person to explain all the details here. But there is an equivalence of categories. These are derived categories. So coherent sheaves, T equivariant coherent sheaves on Hilb N is equivalent to the derived category of T cross Sn. So there's the symmetric group, okay, making an appearance on C2 N. Okay, so what you're kind of doing is you're taking into account this torus action and this quotienting by Sn in two different ways. Okay? So on the one hand, you're using this resolution of the quotient. On the other hand, you're considering objects on the original space, C2n, which have additional equivariance. Okay. So this was a major result that totally revolutionized Macdonald theory, because what happens is you get the following. So this, which induces isomorphism of QT algebras. Okay, so this QQT field is, you could think it's the field of fractions of the representation ring of T. So T is a two-dimensional torus, and so that's what this is. So this is the field of fractions of I'll write it here. R of T, representation ring of this torus, or if you like, the K theory of the point that's equivariant with respect to T. So here's what you get. You get K T Hilb N localized direct sum over all N. Okay. Is isomorphic to K theory of the other side. Okay. And if you put all these together, you can perform standard kind of yoga, and you get to symmetric functions. Okay, so lambda, and what this is through kind of the Frobenius map from representations of symmetric groups to symmetric functions. So this is symmetric functions. Here we have infinitely many variables, yeah. So the n on the left actually corresponds to the degree on the right. So it's a different n than before. It's not the number of variables. The little n is the degree of the symmetric function. But this isomorphism that you get from Heyman's equivalence up here sends the fixed point class to something called H tilde lambda. And this is a cousin of the P lambda. So this is a modified Macdonald polynomial. I think one thing that deters people from this subject is that there's so many different versions of the same thing, and they have their own advantages and meanings. But this is some equivalent object to the P lambda that I wrote down at the beginning. Right? You apply an automorphism of symmetric functions to go between the two. Okay. This one has better properties for certain things. In particular, so this has what's called Macdonald positivity. And that was a major conjecture of Macdonald. So Macdonald positivity holds for H tilde. So Macdonald positivity was one of Macdonald's famous conjectures at the beginning of the subject. And Heyman's approach led to a proof of that conjecture using this geometry. Okay, so there's some higher vanishing going on that explains the positivity of H lambda tilde. Okay, so that's a brief introduction to kind of type A Macdonald polynomials, and then how they're connected to at least one thing, geometry of Hilbert schemes. So, like I said, Heyman's theorem and approach revolutionized the subject, even just for type A Macdonald polynomials, but at the same time, it suggested a generalization in a different direction. Okay, and this is the Wreath direction. Okay, so this has to do with Wreath products and the Mackay correspondence. So, let gamma be a finite subgroup of SL2C. Okay. Then Heyman conjectured shortly after his proof of Macdonald positivity that there is an equivalence as follows. So a derived category of coherent sheaves on Hilb. It's a different M actually. So you need separate kind of parameters here, but the fixed locus. So the fixed, so you take Hilb M and you take the subvariety that's fixed under this finite group action. Okay. And okay, so that's the fixed locus, and then there's kind of a technical thing, which is that that's disconnected, and so this chi tells you a component of it. So this with coherent sheaves T cross gamma n C2 n. So the n and m are different, but there's a simple relationship between them, okay, which I won't necessarily say. But gamma n is a Wreath product group. Okay, so you could think of these as maybe colored permutations. So permutations which are somehow colored by this finite group. And this turns out to be much more difficult. I mean, Heyman's theorem was already incredibly difficult and a monumental achievement. But somehow his methods, that looks like an M. His methods didn't quite give the same result in this case. So it appeared to be much harder. And in fact, it is harder. So this was proved, so there is equivalence, and I'll just be a little bit vague, with properties similar to above. So similar to the ordinary Macdonald case. So fixed points go to some objects called Wreath Macdonald polynomials, and there's an analog of the positivity that you had. Okay, so that was a conjecture, and it's a theorem of Bezrekavnikov and Finkelberg. Heyman's conjecture holds for gamma cyclic. Okay. So these finite subgroups of SL2C are classified by the Mackay correspondence. They're parameterized by affine Dinkin diagrams, if you like, and the cyclic case corresponds to affine type A. Okay. So they proved this using some really deep geometry, requiring characteristic P and very, very difficult methods. So it's not very constructive. Actually, it's not constructive at all. Okay. So Hammond's conjecture holds for gamma cyclic, and this looks like this. So gamma is this subgroup of diagonal matrices with a root of unity and its inverse of order R. So I'll let R be the order. So R is the order of gamma. Okay. So this was itself a major result, but didn't really answer the question of, what are these Wreath objects? What are they? It's a very abstract geometric approach. And so what you get is at the level of K theory, one obtains Wreath, Macdonald polynomials, P lambda gamma. Okay, so they're indexed by the same set, by all partitions. Okay, and that's basically because the T fixed points are the same. This gamma is actually a subgroup of T, and so the T fixed points are the same. The T is the 2x2 diagonal subgroup of GL2C actually. But these are elements. The index is the same. Lambda is a partition, but these are elements in a tensor power of lambda. So you take many copies of symmetric functions, one for each element in the set I, and you tensor them together. So where I is, so these are sort of the same, but there's kind of cultural reasons for distinguishing them. So gamma is the subgroup, and I is sort of its dual group, or I'm just going to say it's the set of irreducible representations. So this set I in this Mackay correspondence is the set of vertices in the Dinkin diagram. So this is the affine type A quiver, and this is its vertex set. Okay. So in this case, just a quick note. Hilb M gamma chi. So what this chi is actually is a representation of gamma. That's what tells you the component. Okay. This is a Nakajima quiver variety. For this quiver. So you have the cyclic quiver, and so let's say 0, 1, R minus 1, 2, R minus 2. So this is my cyclic quiver of any size, and I have one-dimensional framing space at vertex 0. So if you know about Nakajima quiver varieties, that's how these are realized. And it's true in general that the fixed locus of the Hilbert scheme for any gamma, any finite subgroup, any sort of finite subgroup of SL2C, the fixed locus is a Nakajima quiver variety. Okay. And the quiver is the affine, is an affine type quiver, affine type Dinkin diagram that comes from gamma. Okay, so that's the setup for Wreath Macdonald polynomials. But then the question is, the main question that motivated this work is, what are the P lambda gamma really? Can we construct them by some explicit means, not just from some deep categorical equivalence, okay? But how can we really get our hands on them, okay? And this is where these operators come in. Okay, so one thing that's just not at all clear, if you wanted to do something like difference operators for the P lambda gamma, you can't just look at Macdonald's original operator, which kind of had a lot of nice structure to it. You can't just look at that and cook something up, okay? This is too sophisticated. You can't just guess and get it. I mean, we couldn't, and I really don't think you can just guess it. So you need something more. Look, and if I have time, I'll talk about what the more is that produced this. But it's not just a sort of a lucky guess. It comes from an algebraic origin. But let me talk about what these are first. So, so this is OS, my work with Mark Shimizono. And so if you have difference operators, you have to be talking about some finite set of variables. So this is a dimension vector telling you how many variables you have at each vertex in the cyclic quiver. So for each I and I, which are the vertices in the cyclic quiver without the framing, how many variables do we have? Okay, so we have a dimension vector, and then we have variables. So I'm going to call this xn dot, capital Xn dot, xi, okay. The variables are now colored by the vertex. So I have a subscript for the sort of the variable number, and a superscript for the vertex where it lives. So I is an I, and k is between 1 and capital Ni. Okay, these are the variables. Okay, and you have a symmetric group. Okay, so for each I and I, you have a little symmetric group, and it permutes the variables at that vertex. So Sni permutes the variables with superscript I. Okay, and so here's what you can do. So you can project, Wreath Macdonald polynomials are here, symmetric polynomials in infinitely many variables, and you can project. So basically what this is doing is, so this is this finite thing. So QQT, I have my variables xn dot, and these polynomials have to be symmetric with respect to that product of symmetric groups. And so I have this guy, and you're really just plugging in. Okay, so F, you could think F is just a simple tensor. So F is a product of FIs, little Fi, and in Fi, you plug in the variables at that vertex. Okay, so this is just a simple, if you like, if you take a single copy of symmetric functions and you can project to finitely many variables, this is just the tensor product of such maps. Okay. Okay. So this is just evaluation. If you like, you can maybe just ignore this technical point and just think the Wreath Macdonalds are here in this lambda n dot. Okay, so here's what we do. So for any I in I, we construct explicit difference operators, MI. And they're much more complicated than the Macdonald operators, but still I think they're quite beautiful. So the sum is over a set, which I'll describe in just a moment, but it's an alternating sum. And you have some coefficient. And then you have, so this depends on J underline. And then you have this TQ, J underline. Okay. So it looks like the Macdonald operator structurally, but it's quite different. The first thing is it's alternating. This is a subset of I. And this X bar is a choice of variable X, J. Let me make this clear. At J. Okay, so it's a variable in the set of variables, but it has to be positioned at vertex J. It's a special one, so I underline it. This is for all J in J. So basically what I'm doing is I'm just like the Macdonald operator, it was a sum over K, and that K, let me go all the way to the top. That K kind of told you what variable you're working with. So this you could say you're choosing a variable. The sum is overall choice is a variable. This guy down here is sum over all choices of variables, where I choose some variables. So J is not empty. And I choose at most one variable at each vertex. Okay, so I choose an xj underline at J for all J and J. And J is a non-empty subset of I. So I choose some variables, but maybe not all. Okay. And this right here is a rational function, just like the thing. Well, it's not just like it, but structurally it plays the same role as in Macdonald's operator, but it's much more complicated. I won't write that down because I'll have a fit before I get it written down on this iPad. But it is written out in all its glory of paper. Let me tell you what this translation is. So this is a new kind of really interesting feature. So this shift, right? I call this a translation. So I'm going to talk about this below. So here's a typical kind of example. So let's say I have 5 vertices. 0, 1, 2, 3, 4. So R is 5. Okay, and let's say my J is going to be, I'm going to choose this one and this one. Okay, so I'm choosing a subset. I'm going to choose vertex 0 and vertex 3, okay, non-empty subset. And this is all part of this quiver, this cyclic quiver. I'm not considering the framing. But let me erase that. It's getting a little too cluttered. So J is 0, 3. And so what I'm doing is I'm going to choose an X0, and I'm going to choose an X. X3. So choose X3. And what I need to do then is I need to define some quantities at the other vertices. Okay, so this is a really cool thing that I think is totally new about these operators, at least in this context, is that I need these extra things. So the direction is to propagate in the decreasing direction of the quiver. So I'm going to put a variable here, which is q x 3. So I take that one that I chose and I multiply it by q, and I'm going to call this x underline 2. And this one I'm going to say is q squared x3, and I'm going to call that x1. And over here, I have to turn my head the right way. So I need to call this one q x 0. Okay, and that's what I call x4. Okay, so you make your choice up front, the j and the initial x bars, and then you propagate them around the quiver into the empty spaces. Okay. So the circled vertices are where I made initial choices, and then they get propagated around. So this is the initial data. And then this translation, which is a generalization of Macdonald's Q shift, but there's much more complexity here, sort of, or much more choices, says the following. So Q J underline is it's this. So replace X underline J by Q X underline J plus 1. So in this example, this is for all J and J. It's not everywhere. Okay, so at some variables it does nothing. Okay, at some vertices it does nothing. But so I replace here. I would replace x0. So for the example, I replace x0 by q cubed x3 underline. Okay, so this is a new thing, is that you have sort of the cyclic distance in the cyclic quiver, and the powers of q that you see can be higher than just one in your translation operator. So, and then x3 by q x0. So this is kind of a new interesting structure in Macdonald theory that comes out of this. And for gamma equals 1, for gamma trivial, you just have one guy, and it's equal to Macdonald's. So that's a property that our operators have. It's a sort of massive cancellation in the formula to get there. And then, so what's our result? Our result says that these MIs, I and I, act diagonally on Wreath Macdonald polynomials. P lambda gamma, if I project them to finitely many variables. Okay, so the best thing you can hope for, and their eigenvalues are the same basically that they were in the ordinary case, except they're separated. So it's sort of great, everything is graded by I, and so you get the natural eigenvalues that are in fact very useful. So in Macdonald theory, if you want to use these operators to do anything, like Macdonald's original operator, you need to know the operator explicitly and the eigenvalues. And then you can actually do quite a lot with that. You can prove a number of properties of the Macdonald polynomials, like duality properties, Pierre formulas, and things like that. A lot of interesting combinatorial consequences come from explicit operators and explicit eigenvalues. So I don't have much time, but I just want to say the MI arise, just to give you an idea where they come from what's called the horizontal Heisenberg, which is just, it's a commutative algebra, actually. So it's the central charge is just 0. Commutative Heisenberg subalgebra of the quantum toroidal algebra. UQT toroidal. So it depends on 2 parameters, and it's the one for GLR. So R is the number of vertices in the quiver, or in the cyclic group, gamma. And you have a quantum toroidal algebra, which you can think is sort of like a double quantum loop algebra. Okay, so you can think it's like if you haven't seen this before, it's like UQT. So it's 2 parameters, but it's like the loop algebra of the affine Lie algebra. Okay. So this is not the quantum group of a Kac-Moody algebra. Okay. It's sort of one step beyond that, and it has a lot of awesome, remarkable structure and symmetry, and all of that kind of comes in to give these operators. Okay, so I don't really have time to say much more, but that's how we got them. So thanks very much for listening.
So let's have questions from our online participants.
I don't have any questions. Thank you, Oleg.
Yeah, me neither. Thank you.
Thank you very much.
Okay, thank you. So do we have questions from the audience? Okay, so
no, so the question is, could we extend our results to other affine types? And the answer is no. So basically, very, very little is known. Even Heymann's conjecture is not known outside of this affine type A case. Yeah. So it's not even known whether the Wreath Macdonald polynomials exist in that case. That's right.
Is there a representation corresponding to these Wreath Macdonald polynomials?
That's a much more difficult question in the Wreath case. So the sort of, if you try to take the n factorial theorem and naively generalize it, it just doesn't work. And so this does produce bi-graded modules for the Wreath product group. But so just to give you an indication, one thing that happens is that they can have negative degrees. So they're not in a really non-trivial way. So they're not just in the usual Macdonald case, you can actually always work with positive degrees. And so there's the naive generalization just doesn't work. And in fact, it's not known what it should be.
one more question.
Yeah, so in your formula for your operator, there's a sum over J and X. So is J over all subsets?
Yeah, all non-empty subsets of I. Yes, that's right. So it's the sum over all pairs, and J is a non-empty subset of I.
How is it obvious for some reason that it should be preserved like symmetric?
I haven't thought about that. So it comes from this quantum toroidal algebra approach that happens. It preserves symmetric polynomials, but I haven't thought about proving that directly. I think probably because the operator is written down explicitly, that should be possible, but I haven't worked out the details of that. Right. So yes, well, sort of. This quantum toroidal algebra acts naturally on two spaces. One is its vertex representation, which is kind of the symmetric function side. In fact, many copies of multi-symmetric functions. And the other side is this direct sum of K theories. And there's a result of Josh Wen that says these two actions, and also goes back to a result of Sasha Symboliuk, that these two actions are related, but there's a very subtle twist that you need called the Miki automorphism of the toroidal algebra. So the symmetric function side is related to the geometry through this Miki automorphism. What this tells you is that you can construct some operators which are eigenoperators, but in fact, it doesn't tell you what they are. It tells you what the eigenvalues are. That's what it tells you. I can say more, but that perspective tells you that the eigenvalues, but not the operators themselves. Yes, it's you. Yeah. I'm so sorry. Yes, that's possible. Yes. Josh Wen is working on that, so that'll eventually be his result. But there is a natural inner product here that generalizes Macdonald's inner product, and it involves the quiver and sort of rotation in the quiver in a very nice way. So, yeah.
Okay, so let's thank the speaker again.
Maybe we can thank the organizers.